All right, thanks for being here. Nice to be midway through Midway. I'll be talking about pragmatic algorithmic game theory, which is a talk I gave at the ACM EC conference. I adapted a little bit for you guys, but just a bit. So let me start by saying what algorithmic game theory means, particularly to that community. So there was this famous book, this edited book called Algorithmic Game Theory that ended up being sort of an early point around which this field gelled. And it described itself as being research. It described this topic of algorithmic game theory as being about research at the interface of computer science, game theory, and economic theory, largely motivated by the internet. So if you look at the kind of work that was proposed, not just in that book, but in work that has called itself algorithmic game theory afterwards, it seems that this community is particularly interested in the design of new mechanisms, particularly but not only auctions and market mechanisms, trying to analyze existing mechanisms and figure out something about what they do. Particularly a prominent example is sponsored search, where the mechanism kind of predates a formalized design approach, but then there's a question about what happens in it. And equilibrium computation, which of course is a kind of both a very fundamental computational problem and a kind of bedrock tool that you would want to use in a lot of this kind of analysis. So typically, this community has gone for very general settings and attacked them theoretically, as indeed we're all kind of familiar both in economics and computer science. I think they've added a lot over the traditional economic kinds of analysis, yielding both impossibility and optimality results, which maybe aren't that different from what economists would expect to see. They're the same kinds of things economists have proven for years. But added to that kind of repertoire, also the perspective of approximation. And I think really kind of moved the ball down the field a bit from the perspective of approximation, showing, for example, that they can achieve something close to optimal revenue with a simple mechanism or something like that. So broadly speaking, this is what I mean when I say algorithmic game theory, this kind of field mostly within CS, but very much in communication with economics. Unfortunately, I think this field struggles, of course, as any theoretical discipline does, with obtaining the same kinds of clean theoretical results that address complex and realistic problems. So there tends to be this sort of boundary of analytic tractability beyond which it's hard to go. And this approximation framework makes it possible maybe to go further than one might expect, but nevertheless, there sometimes is this experience of hitting a wall and going to something more practical. So the perspective that I'm going to advocate today is what I'm calling a pragmatic approach to algorithmic game theory. And what I want to argue, what I did argue to that community, what I want to argue to those of you here who see yourself as part of that community, is that it's possible to get more traction on the realistic problems that one should be interested in by leveraging one or both of two kinds of pragmatism. And the first is to care about getting good performance only on problems of interest, rather than in relatively unconstrained settings. So to try to drill into much narrower but nevertheless useful categories of problems. And the second is to achieve success in statistical rather than analytical terms. So this means to adopt a kind of data-driven approach in one's work where the problems of interest might be defined implicitly by a data set that gives examples of the kinds of problems one cares about, and/or there may be data-driven measures of performance. So we might be scored on some kind of average measure of performance over a data set, rather than simply you're proving a theorem that says something about how close to optimality we've come. So all of this you can sort of see as a sort of machine learning perspective about how to do the work at the boundary of economics and computer science. So in this talk, I'm going to talk about work that I've done with collaborators that attacks problems that are kind of core algorithmic game theory problems, in the sense that they're the same problems that the algorithmic game theory community has been itself interested in a more theoretical vein, but that's pragmatic in both of these ways. And before launching in, let me just say the obvious, that I certainly don't mean to give the impression that I've invented the notion of being pragmatic about algorithmic game theory. There are many others in this computer science economics community who do the same. And indeed, I think one reason that I'm really happy to be at this workshop is I think that most of you here seem to have this kind of sensibility about the work that you do. So I hope that makes you a receptive audience. And probably the only way I could really piss you off and lose you would be if I gave you the impression that I was the only one doing this. So let me reassure you that that's not what I think. So in particular, I'm going to talk about 3 different lines of work. You can see them up at the top if you have good eyes. The first one I'll talk about is repurposing radio spectrum via what's called an incentive auction, which is something the FCC is in the progress of doing. As I do these kind of slides along the way, I'm just going to kind of call out my collaborators. So my PhD student, Alexandre Fréchette, is my main collaborator here. And Frank Hutter, Holger Huss, Ling Xu, and Steve Ramage contributed to some of the tools that I used in this work. So you guys have probably heard about the incentive auction, but let me just say just a little bit about it. So the FCC had this great idea of having an auction that had something to do with incentives. Well, no, that's not quite it. But the FCC, yeah, what a great name, right? I don't know. But anyway, that's what they call it. So what can I do about that? The FCC wants to basically sell off radio spectrum to mobile phone companies, as they do. The problem that they face is that they've kind of already sold all of it. There just isn't really good radio spectrum to sell anymore. And people still want to watch cat videos on their phones while they're on the subway. So we've got a problem. And the solution to this problem is to take radio spectrum that's being used for something else and repurpose it for use in mobile phones, because that's the use that people now care about. And in particular, it turns out that television, back in the day when broadcast television started up, it got given really awesome radio spectrum because it was kind of the big game in town. And now broadcast television is not that important to people. People are much more interested in getting television over cable or satellite or even over the internet. So it seems like maybe there's some economic efficiency gains to be had here by taking back some of that spectrum and selling it off to mobile phone companies where it can be used more productively. Of course, the catch here is it's not. I'm not a lawyer. I don't fully understand the legal side of these things about whether this is necessary or just a good idea. But it's at the very least a good idea not to just confiscate this spectrum from the television stations and give it back to the mobile phone companies in order to make this all go down in a sensible way. It turns out that what one needs to do is to buy the radio spectrum back from the television stations in order to be able to then sell it off to the mobile phone companies. So this gives rise to the question of how you would go about doing that. How are you going to buy back the right to broadcast from a whole bunch of different television stations, all of which operate at particular powers on particular channels and from particular antennas in given regions of the country in this crazy patchwork all over the United States, and one by one get different ones of them to sell back their right to broadcast and somehow assemble this into something that a mobile phone company would be interested in buying. So that's the kind of underlying optimization problem that is going to form the allocation problem for this incentive auction. So I can tell you this auction is now approved and ready to go. You can see this is the report and order that the Federal Communications Commission just put out, announcing that this was going to happen and giving some details about how it's going to happen. You can see it was just a little over a month ago that this happened. So this is a really current thing. The report and order makes really entertaining reading. I recommend that you sit down with it. It's 488 pages long, and it's written almost entirely by lawyers. So I think it's great. I mean, you here at a business school presumably do this kind of thing all the time. So that should be fun for you. But in case you're not going to read it, let me just tell you a little bit about what it would say. I can sort of put in one slide what the 488 pages say from your point of view as economists. Essentially, there are going to be 2 different auctions that will happen in a linked way. So there'll be a reverse or descending price auction for broadcasters. And in the reverse auction, essentially what's going to happen is stations will be offered some very high reserve price to stop being television stations and instead to be people with bags of money. And they'll say, yes, I would take your large bag of money in exchange for not being a television station anymore. And the FCC will look at all of these offers to stop broadcasting and determine that it would be possible to get rid of a whole bunch of spectrum if that were true. It would be possible to take all of the TV stations that go up to channel 52 and change that to TV stations that only go up to channel 30. And then they could take that radio spectrum that was used for channels 31 up to 52, except for channel 37 if you're one of the people who understands how these things work. Turns out there's something special going on there. Radio telescopes need to operate on channel 37. And you take that big block, and then you can sell that off to the cell phone companies. Because what cell phones need is a big contiguous block of spectrum. They can't operate on little corners of spectrum in different geographical regions. So then you do that, but then you've probably gotten too many people who are willing to accept big amounts of money. So then you start lowering the amount of money that you're offering everybody. And as this amount of money that you're offering goes down, at some point high-value participants might say, I'm not so happy anymore to accept your reduced amount of money. I would rather go back to being a television station. And they would go back on the air. You'd confirm that it's still possible to put them somewhere. And you kind of keep doing this until everybody either is being paid nothing or is indispensable to you and can't be put back on the air. I'll show you that schematically in a minute. Why do you have to go through the government to make this happen? The real reason is, let's say I'm a television station let's say right now I'm channel 13. Or let's make me a UHF station and say I'm channel 15. That's not a piece of spectrum that's going to get given to the radio, to the telecoms. But instead, what could happen is you could take this and take somebody else who isn't a useful piece of spectrum and kind of stick him into my spot. And this ability to move around stations is something that only the government can do. And fundamentally, that's needed to get big contiguous blocks of usable spectrum. So the government is telling the TV stations, this is a one-time chance for you to participate in this auction. And I think that's a pretty plausible thing to say, because this repacking is, it really has to happen on a national scale to be useful. And the government only can do this. They're going to cause slightly different interference on the stations that get repacked. They can only do this because they've been given authority by a law. So this can't really happen just on the side. So this is the reverse auction. The forward auction is then taking this stuff and selling it off to the cell phone companies. So here we're going to have different licenses in every region, and the prices for these licenses are going to increase until supply and demand meet. So you're going to have just a much more straightforward kind of ascending auction. This is not absolutely trivial, but this is kind of the sort of thing that the FCC has been doing for a long time. All right, so we have this reverse auction, we have a forward auction, and then we have some kind of link between them. So we have some amount of revenue that we need to achieve to make everybody happy about what just happened. And if that hasn't happened, then basically we decide that we were trying to clear too much spectrum. And so then we reduce the amount of spectrum that we're trying to clear. And that will have the effect of both lowering the prices that we have to pay because we have to buy out fewer TV stations, and increasing the per unit prices that we will end up charging telecoms because the supply will have gotten scarcer. And so the prices will continue to rise. And so essentially what we'll do is we'll just change the amount of spectrum that we have to clear and then keep running the auction. You might notice that these two prices are not directly related to each other, right? So this is not a double-sided market. Or if it's a double-sided market, it's very indirectly a double-sided market, because kind of what's happening is the government is doing this one auction with everybody and getting all these goods and then kind of glomming them together and turning them into something else and selling them to somebody else. So the government gets to keep whatever the difference is, and the Congressional Budget Office has projected that difference is $25 billion. So the government's take is a bunch of money. So let me tell you a little bit more about the reverse auction, which is going to be my focus. I found in talking to people that there seems to be a lot of misunderstanding about how this auction works. And so maybe you guys all understand it, but I made a very sophisticated PowerPoint animation to explain how this works. And And I say this both jokingly and not. I say it jokingly in the sense that when you see it, you're going to be disappointed. But I say it seriously in the sense that it took me forever to make. So let's see. So it turns out that rather than talking about buying out television stations, which turns out for various reasons to be a little hard to think about abstractly, I'm going to switch to a problem that I think you have more experience with, which is the problem of airline overbooking. Right? So you go to your airline of choice, and they say, sorry, remember that ticket we sold you for the flight that you're on? Well, it doesn't really correspond to a seat on our plane. In fact, it turns out there's this law that for some reason we can sell you things that don't exist. And if you don't show up for the flight, we keep your money. But if we don't have a seat for you, that's just too bad for you. And now we're going to see what happens. So let's think about the part of what happens. And in fact, what really happens is they just screw you and you're stranded in Chicago. But let's imagine something slightly more reasonable that involves an auction. So the way this is going to work is, and for reasons that have to do with this FCC auction, I'm going to ask that passengers either fly in the cabin they're assigned to, or they have to give up their seat. I'm not going to allow passengers in first class to move to economy class. I'll explain afterwards why that's important. So the feasibility constraint that I'm going to have as an airline is that the number of passengers in each cabin is less than or equal to the number of seats I have, because I can't fly with people standing up. Someday they'll do that, but not yet. And I'll use a descending clock auction to set compensations. And the way to think about this is I start with a plane that's big enough to hold everybody. So these dots, which I individually placed with my mouse, are people. And this is my plane, right? So this, by analogy, is the current state of affairs with television stations. They're all the television stations have somewhere to broadcast. The problem is we're going to get rid of a bunch of the spots, right? This is clearing a bunch of spectrum. We're going to lose a bunch of the seats. And now we have people without seats. And this is where the airline decides, hey, we could send a smaller plane and save ourselves some money. So the airline offers compensation. So we say to everybody, we'll give you $1,000 if you just elect not to fly, and we'll fly you tomorrow morning. And everybody gets to make a choice about whether that sounds good to them or not. And so some people say, no, I'm going to hold on to my seat. I'm not going to take your $1,000. And they're on the plane. And some people say $1,000 would be great. Why not? I'll do it. And they kind of go off to the side here. And so here's our state of affairs with $1,000. The thing to notice now is that I've got a lot of empty seats. So as an airline, I think, these guys don't seem to value money all that highly. I made a bit of a mistake offering them $1,000. So let me change my offer. So you say to everybody, remember what that thing I said about $1,000? Really, I was lying. It's only $800. How do you feel about that? And some of them say, well, turns out I only did it because you said $1,000. In fact, I want to go back on your stupid plane. And so now some of them move back. And in fact, in first class, let's say they all move back. So what's going to happen in this auction then is these guys now, these blue dots, have nowhere they can go on the plane, because I'm not going to let them go to a different class. And so that means they've accepted an offer for $800. But I can't make them any subsequent offers because I can't back that offer up with anything. If I was to offer them $700 and they said, I won't take your offer, I would be in the embarrassing situation of not being able to do anything. So I have to freeze them at the last offer they accepted. These other guys, though, I can still do without. So for them, I lower the price. And then some of them move back. And then I lower the price again. And then some of them move back until something freezes again. And now the green guys are frozen because, again, there are no spots for them. So I freeze them at a different price. The blue guys are just gluttons for punishment. That's why they're flying in economy class. So we just keep on hitting them with lower and lower prices. And some of them move back. Like the suckers they are, they'll even take $300. And eventually $200, a couple of them move back, and these guys get frozen. And so this is how the auction works. So basically, we're going to keep on lowering prices on people as long as it's possible to accommodate them back where they were before. And then basically, the willingness of other people to eventually participate in the auction or quit is what's going to drive the prices for you. OK, so what does this correspond to in reality? You might think this corresponds to sort of good spectrum and medium spectrum and bad spectrum, but that's really not true. What I want this instead to correspond to is different places. So there's nothing special about first class. It might have been that first class got a worse price than business class. What's really special is that you can only go back to the place that you originally were, and that there just are different constraints in different places. So let's say first class was really New York, economy class, sorry guys, it's the Midwest. And so we just have different feasibility constraints in different places, right? So it might be that New York kind of locks up early because there are a lot of constraints in the New York region where prices are just falling and falling in Chicago because you have lots of open space out here. Now here's the thing about the real problem. The feasibility constraints, in fact, are a crazy jumbled mess, right? So this is a picture of the feasibility constraints. It might be a picture made by Nick, actually. I'm not sure. Did you make this picture? Thanks for the picture, Nick. I never thanked you properly. I want to take this opportunity. So yeah, OK, that was special. OK, so this is a visualization of the real constraint graph. And what you can see from this is just kind of that it sucks, right? There's just lots of lines everywhere. But in particular, what you can sort of imagine from this picture is every dot is a station, right? And a line is these two stations somehow constrain each other on what channels they're allowed to be on. And because there's just not a lot of nice kind of symmetric cliques in this graph, everything has just got weird stuff hanging off the side. And that means that my nice story about kind of everyone in economy class is the same and everyone in business class is the same is not going to be true in this graph. The question of whether you can personally go back is going to be a personalized choice for everybody. The point means there exists a constraint between those two stations that either they can't be on the same channel, they can't be on adjacent channels, they can't be on certain same or adjacent channels, but they're allowed to be on other ones, or some combination of those sorts of constraints. And there are many channels, so typically we're not going to clear all the spectrum. So any two channels linked by an edge can still both be accommodated, but eventually they're going to start to constrain each other as I reduce the set of available channels. So here's another visualization of this graph, which is maybe a little bit easier to think about because this one has the advantage that it looks like the United States, but the disadvantage that you can't see just how awful the New York region really is. It's really awful. It has nodes with degrees above 200. So there's some really, really densely connected parts of this graph. This just sort of blows it out in a way that gives you a better sense of the connectivity of the graph. So there's this underlying computational problem if I want to do this kind of airline algorithm the way I showed it to you, this descending clock auction, which is asking for a given set of people that I think are going to participate in the auction that have currently accepted going off air, and another set of people that I have to repack because they've exited the auction or they never participated, is it possible for me to also not take you? For every given person, is it possible for me to put you back on the air and somehow readjust the stations I give to everybody so that the whole thing works? And if so, I get to lower your price. And if not, then you're frozen. And I have to take the last price you accepted. And in a sense, you're not participating in the auction anymore. And so this is this computational problem that I'm going to have to answer every time I want to consider lowering a price for every single station. So I'm going to have to do this kind of on the order of 2,000 times every time I tick the clock. And bad news, this is the part where computer scientists come and bum you out, because this is an NP-complete problem, which the theorists will tell you means that you should go shoot yourself in the corner because nothing can be done. With Chicago, somebody can shoot you for you. You don't have to do it yourself. But you should be very sad. The pragmatic truth is, just because a problem is NP-complete doesn't mean you can never solve it. It just means you can't be confident that you can always solve it. So it turns out there are whole kind of research communities within CS about finding practical ways of solving NP-complete problems, and they work all the time. Google wouldn't be making a self-driving car if it weren't possible to solve NP-complete problems with decent reliability all the time. You just can't do it absolutely all the time. That's why the car will sometimes crash. Sorry. Or something. So here we've got a graph coloring problem with 130,000 pairwise relationships between stations, something on the order of a couple of million actual constraints which speak about individual channels. And the FCC was initially pretty skeptical about whether this problem could be solved at a national scale, and they were doing a bunch of pretty hacky things to try to make the problem smaller. In the end, we're solving this problem exactly and at a national scale using some tools from empirical algorithmic. So I'll tell you a little bit about how we're doing that. basically the bunch of tricks that we've got are to use a SAT encoding, automatic algorithm configuration, and algorithm portfolios. So I'll tell you kind of a slide about what each of those things is. So OK, so what do we do with this thing? Well, how many of you know what propositional satisfiability is? Hooray for you. OK, you guys can get a coffee. Let me spend like 30 seconds telling the rest of you what propositional satisfiability is. This is one of the awesome problems in computer science, right? This is part of the bread and butter of computer science. This is like the Corno, whatever it is, Corno something something. What is it? It's like Corno competition or something. Yeah. So that's why I'm a computer scientist. Anyway, yeah, please edit that part out of the video. We don't want that going on. Milton Friedman would be so unimpressed with me. OK, so basically satisfiability is what is actually the first problem that was shown to be NP-complete, or it's in the first little kind of set of problems. And it's really easy to think about because it's so simple. And that means that there are some really powerful algorithms that work with it because the problem itself is so simple that you can really wrestle with it in great detail. So it's sort of a pure combinatorial problem. It says, I've got a set of variables, and each variable can be true or false. Then I can make literals, which are the variables, either the variables themselves or the negations of the variables. I can make clauses, which are disjunctions of literals. So a clause is something like A or B or not C, right? So it's a disjunction of either variables or negated variables. And then I make a formula, which is a conjunction of clauses. So I end up with something that looks like A or B or not C and D or E or not A. So I make this whole string of propositional variables connected with ands, ors, or nots in this particular way. And the question that I then ask is there some way of assigning values to each variable from true or false that make this whole logic formula evaluate to true? And your first impulse might be, well, sure, that sounds really easy. I can just come up with true and false values, and then I know all about logic, right? I know how to evaluate this thing and figure out whether it's true or false. And indeed, it's very easy to come up with some assignment of true and false values to all the variables, look at it in the formula, figure out if it's true or false. But then you might notice, well, if I've got n variables, there are 2 to the n assignments of truth values to those variables. And I could try each of them and test it. But is there some more principled way of figuring out which of those 2 to the n things I have to try? Or do I have to do all of them? Well, if you can answer that question, then there's $1 million waiting for you at the Clay Mathematics Institute, because that would involve answering the question of whether p is equal to np. So we don't know. But so far, we haven't found a way. So far, more or less, you have to try everything. So this is sort of the combination lock of combinatorial problems. You just sort of have to grind through everything. Or sort of, in the worst case, it seems like you have to. But in practice, maybe there's a lot of structure in your problem, right? If I gave you something like A or not A and all kinds of other stuff, maybe you could look at that and say, well, that's got a contradiction in it. That first clause simply can't be satisfied. So I don't need to grind through all the other stuff. I can just spot that contradiction. That's a very simple example of the fact that you don't always have to grind through everything. And there are much richer reasons why you might not have to grind through everything. So that's this kind of empirical algorithms framework. You can't do it for the worst case input, but you can do it for everything else. So how do we formulate this FCC problem as a SAT problem? I'll just do this kind of at a high level. But basically, we say every station has to broadcast on one of its allowable channels. That gives me a constraint that looks like this. So one of these, at least one of these variables has to be set to true. The variable which says this station broadcasts on this channel. So the disjunction of all of these variables has to be true, which means at least one of them has to be true. Each station only gets to broadcast on one channel. That means the negation of each pair of values that station could take disjoint. So at least one of them has to be false. At least one of every pair has to be false. So far, those two things just say every station gets one channel. That doesn't seem like I've done something very complicated yet. But the interference thing is the hard part. So then I take all of these pairwise interference constraints, and I throw them all in. So I say, you can't be on channel 17 while I'm on channel 18. And I do that 2.5 million times for all of the pairwise interference constraints. And I just throw them all in there too. And then I give this thing to a SAT solver with all of its glory of tens of thousands of variables and 2.5 million constraints. It turns out as A side note that most of the clauses have only 2 variables in them, you'll notice. Only this first kind of clause that I gave at the top has more than 2 variables in them. And that's a really powerful thing for a SAT solver, because when one of the literals gets set to false, I can infer that the second one has to get set to true, or the whole thing's not going to work. That's how I could see the contradiction doesn't work, because if one of them gets set to false, the other one actually the contradiction does work, doesn't it? Never mind. Anyway, other things don't work. Yeah, maybe I don't have a 1 variable example. But anyway, when one of these things gets set to false, the other one has to be true. And then I know how this thing gets set. And it might appear in other formulas. And so then I can plug in its values in those other formulas. And that can cause other things to get forced. And I can get these chains in something that's called unit propagation, where I go grinding through without having to do search, setting all kinds of variables. And that's kind of a powerful thing. So basically, we get this crazy thing. You might think on the face of it, it's so ridiculously big, right? I've got like tens of thousands of variables. And in the worst case, I think this thing is exponential in the number of variables. So how could this possibly work? The trick we're going to use is something that my research group has been working on pretty hard for about a decade, which is called algorithm configuration. And the idea is that it turns out that heuristic algorithms, which is what we're talking about here, algorithms that don't come with a worst case performance guarantee, but that sort of embody things that seem like they should be good ideas, which is what a heuristic is, tend to have a lot of parameters. As you're building this kind of algorithm, you tend to face a choice about how much preprocessing should I do? Should I branch this way or that way? Which variable should I consider first? And the authors of these algorithms can and typically do expose those choices to the end user as parameters so they can be changed at runtime. So something that you might do, if you know that you have a given distribution of problems that you need to attack, is to set those parameters in a way that works particularly well for your problem, so that you effectively custom design an algorithm that will work well just for you. And so that seems good, except if you've got something like 100 parameters, setting these things by hand by repeatedly running the algorithm and having it take many hours and then seeing how it did is a pretty hard thing to do. So we've been working on what we call meta-algorithms, algorithms that take other algorithms as input, run those other algorithms many times, essentially do a statistical experiment design on these algorithms, figure out kind of what's going on with them, and explore the space and eventually find some parameter configuration that works really well. You might be skeptical that such a thing could be made practical. It's beyond the scope of this talk to say much about how that works, although I'll say one thing. But suffice it to say that this really does work pretty well. So kind of intuitively, how do we do it? Let me give the example of a single parameter, which is small enough that I can draw it on the board here. So let's say I have a parameter x, which affects the performance of my algorithm. And I have a parameter y that I want to minimize. Think of y as something like the log of runtime. So I'm trying to make an algorithm whose runtime is minimized on the same instances. So I'm running this over and over again on the same problems. So let's imagine that this red line in the graph here is the true performance of the algorithm as a function of x. And of course, I don't know that. If I knew that, I would just minimize that. But I don't get to ever observe that. What I get to do is run the algorithm at particular points and observe its runtime at that point. So these blue circles are places where I actually observed the runtime of the algorithm. Then what I do is I fit a regression model to all of this. I use a fancy kind of non-parametric regression. In this case, I'm using something called Gaussian process regression. The advantage of Gaussian processes is they give me uncertainty estimates. Well, they're non-parametric, so they're arbitrarily wiggly, which is important to me. And they give me uncertainty estimates, which are small at points that I've observed, because I know what's going on there. And they get bigger as I get away from points that I observed. So these gray ellipses are the uncertainty estimates at every point. And so what you'll see is, right at the blue points, the uncertainty estimates are small. And as I get away, they're big. Then what I do is I try to find a point that looks like it would be good to evaluate, a point that I haven't seen yet that looks like it might be better than anything that I've seen before. And what would it take to maybe be better? You want to both be pretty low on the line and also have pretty high uncertainty. And so that criterion is called expected improvement. What's the amount of improvement that I could gain conditional on being better than the point that I've got now? So the green line that I'm showing you is a scaled version of expected improvement on this line. And you can see a good place to evaluate would be right here, according to the line. Because I have high uncertainty at that point because these 2 points are pretty far apart. And also the line is pretty small. So here's a point that kind of makes a good trade-off between the height of the line and the amount of uncertainty. So I would then do another experiment right there, and I would learn that in fact it's not as good as the point to its left. But then I would update my uncertainty estimates so that I'd have another point. And then I would end up, my second choice would be to go here, which really is a minimum, or close to a minimum, and I'd learn something good, and I kind of keep going. So that's how this sort of search guided by a learned model in real time kind of can work. So this is this thing we have called sequential model-based algorithm configuration, or SMAC. That's how it works. OK, so that's the idea of algorithm configuration. And then I have the idea of making an algorithm portfolio, which essentially says different solvers have different areas of strength and weakness. So why should I have to commit, just like a financial portfolio, why should I buy only one stock? Why should I have only one algorithm in my back pocket? Why not have access to many uncorrelated algorithms and thereby leverage the fact that the average of mins is different than the min of the average? So basically, we leveraged this idea too. We built something called SATzilla, which is a portfolio of SAT solvers. This is a pictorial representation of what it does. It's destroying Tokyo in this picture. And basically, this has become just kind of a dominantly successful strategy in the SAT community, whatever that is. So basically, we took all of these things together, and we built a SAT solver for the FCC's problem. So I'm going to kind of conclude here by showing you experimentally what did this do on the FCC's problem. And here's so I need to show you how this graph works. So this is the runtime. So basically, I'm given some distribution of instances that arose in simulations of the auction that really, to our best knowledge, reflect what might happen in the FCC's auction. And I've got problems of up to 1,133 stations, which means tens of thousands of variables in the SAT encoding on the full USA interference graph. So I take those problems, and then I run various SAT solvers on them. So in the upper left-hand corner, these are the names of different SAT solvers that I ran. And I'm showing you a cumulative density function here, which says the probability, basically the fraction of instances that got solved within every amount of time. So looking, for example, at this blue line, which is a solver called clasp, after 10 to the 0 seconds, so after 1 second, it had solved nothing. After about 2 seconds, it was starting to solve things. After 10 seconds, it solved a little bit more than 10% of the instances, and so on. And then we ran it for 5 minutes. We ran everything for 5 minutes. So after 5 minutes, we just stopped them because we're not made of time here. We have to stop it at some point. And you see that the best of the solvers got maybe 45% of the instances solved, which is already kind of good. I mean, something I should point out is that if you don't solve something, you can just call it impossible. You can just freeze that station. And that basically costs you money, but that's OK, right? There's nothing that goes wrong from an incentive point of view. If somebody gets frozen early, you just pay them too much. And as a computer scientist, there's something really beautiful about that, because there's a trade-off between how well you can solve the problem and how much you have to pay people. So you can really go to the FCC and say, if I can give you 1% better SAT solving ability, I'm going to save you $100 million. And normally in the SAT community, you don't get to say things like that. So that's pretty cool. Normally, you can say, if I can do 1% better, I can write a paper in the SAT community. OK, so basically, we added a specially configured version of clasp. We built a specially configured version of clasp. Why do we pick clasp, which looks like the worst thing here? Basically, because it was designed by its authors to expose a lot of parameters. So it was designed to work really well with this configuration kind of approach. And so it's really suited to this. And we built something that worked dramatically better. So this is now solving about 75% of the instances within 5 minutes. So that's already looking pretty good. We then basically did both a bunch of engineering and added some kind of portfolio ideas to this, and built something that we call SATFC, which is for feasibility checking, which is this red line. And this is the thing that we've made available to the FCC. And you can see this is stochastically dominating everything else by a pretty healthy amount, partly just by dealing with very easy instances very quickly. There are a lot of very easy instances. But we're now solving just about everything, all but about 2% of the instances within an 8-hour cutoff. And so this already gives you some sense that there's only so much to be gained by parallelization here. There are only 2,000 stations that need to be checked per round. So what does this look like? Most of the problems were satisfiable. The blue bars here are points where it was satisfiable. The red bars are points where it was unsat. The gray bars are points where we timed out and didn't know. And you can see we timed out in about 1% of the instances. So this is the last slide that I'll give you. So far, I've talked about a situation where we have people either going off the air or staying on the air. In practice, those of you who are old enough to remember televisions as compared to computers, and particularly televisions that you actually accessed on the air, might be aware of the fact that there's something called UHF and VHF. There are different kinds of television spectrum. And you might remember that VHF is kind of bad relative to UHF, right? It's sort of a grainier picture. It's not quite as good. And so it is now. We really have both of those kinds of spectrum. UHF is the stuff that we actually want to sell to the telecoms. That's more appropriate for them. So one thing that we might be able to do is say, the UHF stations could, instead of going off the air, maybe we should pay them a lower amount to accept a lower quality good, to accept VHF spectrum instead of UHF spectrum. And then that's another way of freeing up UHF spectrum. So maybe we should give them these multiple options. This is tricky, and then of course I can do cascading things. Like I can buy out a VHF station, thereby making some VHF spectrum available, and then I can get a UHF guy to move into that. And if those two moves are cheaper than getting that one guy to go off air, maybe that's a better thing to do. And in fact, there's not just VHF, but there's upper VHF and lower VHF, which are themselves different. So there's really 3 bands of spectrum to care about. The problem is doing a design on this kind of space involves multi-minded bidders. It involves bidders who have values for now multiple things rather than just going off air. And that makes the auction design much more complex because, as all of us know here, auction design for multi-minded bidders is much more difficult to think about than for single-minded bidders, except in this kind of glorious point case of VCG. So this has been an area of active study for the groups working with the FCC. Right now, there are a whole variety of different proposals on the table. I'm happy to kind of talk to you about some of the ideas here. I've, in the end, ended up proposing something which I'm kind of excited about, but I'm out of time now, so I'm not going to tell you now what that is. Instead, I will just conclude. If my computer worked the way I thought it did, I'll just conclude here. So there we go. So I guess I've told you about the way the FCC incentive auction worked. If you're interested, let me say sort of one sentence about what these other things are, and I'm happy to talk with you about them on the coffee break. One of them is this idea of what I call computational mechanism analysis, which basically means using computers to analyze existing mechanisms by solving exactly for their equilibria on samples from a valuation distribution of interest. So we can think about something like sponsored search auctions and ask, how efficient is some given mechanism, or how much revenue would it give me on expectation given different settings of a reserve price parameter, or something like that. So that's what I call computational mechanism analysis. It basically works on the fact that there now, as of maybe 5 years ago, exists some really powerful techniques for finding the exact equilibria of compactly represented games. So that might be a technology that would be interesting to some of you. So I just want to throw that out there. The last thing is about a kind of sabbatical project that I worked on in Uganda for building a cell phone-based mobile market for agricultural commodities, allowing subsistence farmers to sell surplus produce to traders in the cities using a kind of Craigslist that runs over SMS, which is effectively a kind of double auction. So if you're curious about the application of economic theory to development problems, I'm happy to talk about that too. So thanks for your attention, and let's all have lunch. Cheers.